Hello and welcome. I'm George. I'm the project lead for PriMIA, and in this sort of unstructured, unscripted screencast, I'd like to give you an overview of the library, do a little bit of a walkthrough through the code, and show you how to do a couple of things with PriMIA. So let's first of all talk about what PriMIA is. As you can see, PriMIA is an open mind project. It was developed by people at the Technical University of Munich, Open Mind and Imperial College London. PriMIA stands for Privacy Preserving Medical Image Analysis. So it's a framework for doing privacy preserving machine learning, and it's tailored for medical data in general and medical imaging data in particular. We've got some really nice documentation, which you can find here at this address. And of course, this will all be linked in the description below. And at the time of recording this, the library is not yet publicly released, but it will be very soon in October. And then everybody will have access to the GitHub, and you can go and clone the repository. And after you clone it, you will be essentially presented with these folders here, and I'll quickly talk you through the parts of the library and through what you can do, and we'll have a look at the documentation together and see what PriMIA can do. So once you clone the repository, you'll find these folders and these files here, and I'll just briefly talk you through one by one. You can also find sort of the short version of this documentation here in the documentation for the individual components, or you can just sit back and let me walk you through it. So the configs folder holds configuration files. These are .ini files in the torch directory. These are meant for training, and I'll show you where they're used. And the web setting folder holds some CSV files, and these are used for setting up nodes for training and for inference. And I'll show you how these work in a bit also. The data directory holds all the data from the pediatric pneumonia dataset. That's the dataset we use to do the case study that we're showing in our publication, and that's provided alongside the repository, so you can actually use some real-world clinical data, some real medical data to do your experimentation. So PriMIA is designed to do experimentation on your local computer, but it scales up quite seamlessly to cloud environments, and you can do training over the web, and I'll show you how to do all of that. So let's look perhaps at an image. If you look here at the training folder, you'll see there's some chest x-rays. These are chest x-rays from children, so pediatric chest x-rays, and they belong to one of three classes: bacterial, normal, or viral. And there's about 5,500 images or 5,000 images, and there's also a test set, which is about 600 images. This server simulation folder will not exist when you clone the repository, and I'll show you how to generate it in a bit. There's also some metadata here. These are the labels, and these are sort of the ground truth labels which come with the data sets. You won't need to interact with any of these. These are just used internally. Okay, docs you can ignore. Basically, this is the documentation source for the site you just saw. Figure scripts you can also ignore. These are scripts for reproducing the figures we created for our publication. Model weights is also a folder which won't exist from the start. It will get generated once you start training a model, and I'll show you how this happens and what happens, but this won't exist if you clone the repo. Node, this is quite an important one. This is all the logic for the federated training nodes. So these are PyGrid nodes, and we have modified them to be able to load medical data and to essentially serve the purpose of being a model owner or a data owner or a crypto provider, and to be able to be deployed quite easily. And I'll show you how to deploy these in a second. This site folder will probably not be visible when you clone the repo. That's generated automatically for the documentation. Now Sift, this contains all the source code for PySift, and we're using a custom version which is based on Sift 0.2.9. And unless you really know what you're doing, you shouldn't be fiddling around inside this. TorchLib, this contains all of the logic for PriMIA in the background, so let's just quickly go through them. This data loader file here or module contains all of the data loaders and the augmentation logic, and our sort of main data loader is this combined loader, which is able to load medical data with this DICOM loader here, to which it delegates, and it can also load all sorts of just regular imaging data. And there's some magic here to transform images from 1 channel to 3 channels, do various transforms. We use albumentations to do transforms, calculate dataset statistics, and there's also some stuff for MNIST, and I'll show you how to work with MNIST in a bit. And that's basically this module. You probably won't need to do very much in here. Let's move to DICOM tools. DICOM tools is quite well documented, and it's essentially the interface to load DICOM imaging. So in case you don't know, DICOM is a very common medical imaging format, and it's got a lot of sort of interesting properties and tweaks, and it's not always very easy to work with, and we try to make it as easy as possible by providing sort of these pre-made tools here, and if you want to use DICOMs or modify them, you can find that here. Find config, this is actually a script. It's a convenient script to do a hyperparameter optimization. We use Optuna, which is a very nice library, and I'll show you how to use it to do hyperparam search in a bit, but basically this has got some sensible defaults, just so you can do search over all of the parameters for the model, and you can do this locally. You can do it in a federated setting with virtual workers. That means you can basically run federated learning on one machine. You can do it with WebSockets or HTTP, either on your local machine or over the network. And this is what this script does. The models module contains all of the models that we are supporting. Essentially, we've got 3 pre-made models. We've got a VGG style model with batch norm. We've got there's this one here, VGG 16. We've got a model called SimpleConv, which is just a very simple, small convolutional network. And we've also got ResNet, and that's a ResNet 18, which is the one that we use for everything. And we use it because it's basically a very nice trade-off, I guess, between number of parameters and performance. It's really good. So if you want to use other models and need to access the Torch Vision models, you can do so from here. Not all of them are supported in PriMIA, but they can be sort of patched in with minimal effort, and you can add models here as well. Run WebSocket server. This is also a convenient script. This basically just easily or simply opens up some ports and starts up some WebSocket node clients, so you can essentially simply do federated learning using the WebSocket or HTTP protocol, and you can start it from here. So this is not something you would be using in production. This is something that's essentially here for prototyping, debugging purposes. It just fires up a couple of workers for you, and I'll show you how to do it in a bit, just so you can experiment easily and quickly. Utils, this is really like the 10-ton hammer here. This contains basically all of the logic. So there's stuff for learning rate scheduling. There's namespaces with all the arguments. There's a lot of stuff for augmentation, mix-up, for example, which we have implemented as an augmentation technique. There's modified versions of various loss functions. to work with Mixup, for example, we've got facilities for doing federated, class-weighted averaging, also class-weighted gradient descent. There's stuff for turning on and firing up PySift. There's a lot of stuff related to training and some sort of secret source here, which does secure aggregation of dataset statistics. This is all described in the paper, and you'll be able to work with it. It all happens behind the under the hood, so you will never need to interact with it. But there's a lot of sort of small things which you can discover if you really drill into this module here. These are some standard federated training, federated learning methods. For example, federated averaging. This is just bog standard federated averaging. We have some, I guess, extra tricks with secure aggregation happening, and I'll show you that in a second. This is the main train loop for training with federated learning. We've got secure aggregation on by default. You can turn it off with a command line flag. And this is the aggregation method here, where models essentially get securely aggregated with the FSS protocol. This is the one we use by default. You can change it here if you want to use something else. This is for sending models to the workers, and there's also some deprecated methods which are left in for compatibility purposes. This is the main training loop, and this is just for fancy printing out of some dataset statistics and for testing on between the epochs. So that's that. And save model is whatever needs to happen to save the model weights to this model weights folder. I'll show you what happens there in a bit. Git ignore, you should know the init doesn't actually contain anything, it just suppresses a login message, so don't need to worry about that. The dataset license, this is quite important. It's different from the code license, please observe that if you want to reuse the dataset, you need to reuse it under the terms of this dataset license. If you want to reuse the code, you must reuse of this license file here. Okay. Doc requirements is just what we need to build the documentation. Environment torch is important, and I'll talk about it in a second when we talk about requirements. Also this requirements.txt here. But let's talk quickly about the three main files here. These are inference, test, and train, and let's start with train. So train is basically the main training loop and contains all of the command line stuff to do federated training. And I'll show you how to use it in a second. You basically don't need to interact with it. Everything you need to do, you can do from the command line. But there's a lot of interesting stuff in here. For example, you can see where differential privacy is implemented. You can see what happens with the various flags, with federated, unencrypted, or encrypted aggregation, and the metrics that get reported. We also have training monitoring with Wisdom, which is this nice library. Let's see where it is, Wisdom. Yeah, so you can actually fire up this Wisdom server and it can monitor your training, and it's implemented for these various models here. And last but not least, we've got this main block here, this main clause. This is essentially where all the magic happens. And so that's the train module or script, I guess. Then there's test. Test is a convenience script. It shouldn't be used normally because this is it's not what PriMIA was designed for, essentially. But this is useful if you want to check your results and are using the same data set as we used. So this is essentially specific for testing a model you've trained on this data set, and it'll actually check if the data set matches the data set that we used. So this is not the entry point for doing any sort of inference. This is just a convenience script for working with a case study data set or with MNIST. And that's the purpose of that. And there's also inference, and inference is the main inference loop. So we'll go through how to do inference in a bit. So this is basically all of the core logic we use to perform remote encrypted inference. and you can do that over the network again. You can use WebSockets or HTTP. You can also use virtual workers in case encrypted inference over the network is too cumbersome for you or too expensive. It's quite data I/O intensive and quite slow at the moment because of the huge amount of operations. And if you want to just do experimentation with how to do encrypted inference on real data, but want to use virtual workers, you can do that from here too. And this is basically only just a loop for looping over the data set and producing the results. So in our case, we sort of set it up as an endpoint, or I guess the idea is that the data owner initiates a request to receive a result, and essentially they get back some JSON and or they get back an encrypted result and they decrypt it and it's passed as JSON, so it can be nicely displayed on a website or inside an app. Okay, so that's that, and let's perhaps first talk about how to set up the environment and the requirements. So we strongly suggest using Conda. Conda is much better than at handling dependencies than pip, and we've got this environment torch.yaml file here. So if you want to recreate the environment, you need to create a new Conda environment, and you can pass the -f flag. I think it's Conda env create, in fact. -f and then environment torch.yaml, and this will create the environment, including, in fact, the correct Python version, which is Python 3.7.1. So Python is actually hard-coded here. Now, if you don't want to use Conda for some reason, there is an alternative method which is not supported, but it is present, and it's using this requirements file. And you can do it with pip install -r requirements.txt, and that will install all of these requirements. Again, please make sure you've got Python 3.7.1 installed. Other Pythons are not supported. They might work. I've tried it with Python 3.8. It seems to work, but we can't offer any guarantees for that. And please make sure that you don't install PySift before installing these requirements. That's why Sift is commented out here. So after you've installed the requirements, then pip install -u Sift, and you need version 0.2.9. So this will install the requirements for PySift and PySift itself, but during use, there's a lot of stuff which will happen with our custom Sift version. So this is still a bit experimental, and as we're moving in OpenMind, we're moving to Sift 0.3, and we found this is the easiest version easiest way to actually realize that without driving users completely nuts. So yeah, that's the way to install the requirements. And once you have the requirements, you will have, I'm assuming you used Conda. It's a sensible choice. You can use mini Conda, by the way. You don't need Anaconda if you just want a bare bones Conda, like small Conda package without any packages. The package will be called Torch 4P, and that's the one which includes all of the requirements that you need. Okay, so we have a make file, which is super useful. There's a huge amount of stuff in here, and basically anything PriMIA can do, you can probably do just using the make file. So you can just do make install to do the environment thing I just walked you through, an update also in case we issue an update, and we'll update this environment torch.yaml file. Doc install you shouldn't need to fiddle with because it's just for the documentation. Then there's this block here with cleanup. This is sort of the danger zone, and if you sort of mucked up your environment or you've got stuff lying around, you can go make clean all, and that will actually delete all of the folders that I mentioned before. So for example, we'll delete this model weights folder, and it'll go into this data folder and clean out all of the data the server simulation folder. So be really careful. This will destroy the model weights also, right? So it will go in and without asking you, it will remove the model weights folder. So be really careful. If you want to be more granular, you can use one of the other ones. Now, if you want to reproduce our results or experiment with the data set that we used, we've got this block here, which is create datasets. And this is actually quite nice. This automates all of the data distribution, so you don't have to take care of actually moving any data manually from folders to other folders or from moving them to other computers or whatever. You can just clone the repo on every computer you want to use, and then you can ask the node to make server folders. And what this will do is actually copy and paste data from the original data directory to this server simulation folder. And I'll show you how this works. After this happens, if you go to data server simulation, you've got worker 1, and it's got a subset of the data. Worker 2 got a subset of the data. Worker 3's got a subset of the data. And there's a validation set, which is supposed to be local. So this actually copy-paste data, so this uses up a lot of space. And if you are intent on just remaining local, you don't need to do that. You can do something which is much faster and saves a lot of space, which is to make symbolic server folders. And that will actually just symlink the data. So these are not real files, they're just links to the original data set here, and this will save a huge amount of space. So this is what I suggest doing. And there's also a way to create a super small data set, and that's to make minimal server folders, if I can type. And this will by default create like a super small data set of 4 images per worker and the validation set of 4 images. This is obviously not meant for any serious training or validation or anything. This is just if you want to try something out and you just need a couple of data sets and you need to debug something, you need to run something, and you can change this number here, this 4, and that will adapt the amount of images that are put on these folders. So we'll stick with that now, with these 4 images per folder, so we can actually watch like an entire training loop. Otherwise, if we train through 5,000 images, this will really take a very long time. Okay, so these are all the training ideas here, all of the training functions that PriMIA has, and these are also available from the makefile. So I'll show you the makefile way first, and then I'll show you the manual way, how to do it. So if you just want to train on virtual workers using secure aggregation, you can just run make federated secure. So what this will do under the hood is it'll run the train.py script. So let's have a look at the options for train.py. And you can always get help with the -h or --help flag. You'll get a nice welcome message. I'll just enlarge this terminal a bit so we can see. Okay, so train.py has the following flags. It wants a config file, and that's a configuration file. And these can be found, again, the templates for them. You can put it anywhere. You can link any file on your computer. But there's some samples here, and we'll go through them in a second, how these are built and what they consist of. Then you can pass --train federated, which is to train with federated learning. And if you don't do this, this will just train locally. So this becomes normal PyTorch. And if you train locally, you can also go and pass the CUDA flag, and that will use your graphics card. If you go train federated and put CUDA, you'll get a warning and it won't work. That's because PySift at the moment doesn't support training on GPUs, and this will be added in the future, and it'll work. By default, it'll use encrypted aggregation or secure aggregation, and if you don't want that, you can turn it off by going unencrypted aggregation. It also wants a data folder. Now, this is obviously for the case that you're training you're simulating training with virtual workers, and if you created the data directory as I showed you before with a make file with make minimal or make symbolic server folders, you'll have this data server simulation directory. And if you go and pass data server simulation, it will use these images. Alternatively, you can pass MNIST, and then MNIST will be downloaded and used instead. That's if you've got like just a little laptop or a computer which isn't that powerful and you can't use all of the the big images. You can just do the same with MNIST. If you pass Wisdom, it will use Wisdom. For that, you need a Wisdom server, and there's some documentation for how to do this. That's down here, training with Wisdom. And if you also go on the Wisdom site, there's a lot of tutorials on Wisdom down here. So just click on the link in the documentation, and that'll take you to the Wisdom site where you can see how to use it for monitoring training. Great, Kudo, we talked about resume checkpoint. That's if you had to interrupt your training and you've got a model checkpoint and you need to resume training from it. Verbose just prints out a few more debug messages. It's not necessarily needed. Save file, you can pass a file name for the arguments and the results. So this will actually print the arguments that training uses, which are in the configuration file, which I'll show you, and the result of the training, that's the metrics, into a CSV file. And you can name this training in a particular way, otherwise it'll have a weird name like federated data from training simulation, something or another, and a date stamp. So you might want to suppress this. So this is sort of how train.py works. And if you're, if you're lazy and you just want to see it work, you can just go and do make federated secure, and that will just fire up PriMIA automatically, and it'll just start training, right? So right now it's augmenting the data on the workers, and then it'll start training, and you can see the training animation change in batches, and it securely aggregates every preset number of batches, and it'll give you this really nice table where it shows you the confusion matrix. It'll show the percentage of the images classified correctly, and macro and weighted recall precision and F1 scores, micro recall, the Matthews correlation coefficients, and ROC AUC. So this is now running an epoch of federated training or federated learning, and right now it's synchronizing, and that's it. And now it's moving on to the next epoch. And as you can see, model weights now has been created, and it saves the weights here. And this is just a .pt, that's a PyTorch weight file. So this will just, you can just use it later for inference, for example. Okay, let me just kill this here. And you can do the same with unencrypted aggregation, which is by passing federated insecure. You can also do the whole thing on grid nodes. So if you want to see how this works, there's two ways. You can either go in and run the node module, and you can do this by running python-m node, and this will give you the options for firing up a grid node. So if you're a data owner and you're on a site which has some data they want to host, you can run node here, and there's some options here for the port that you want the node to use, the host IP, the grid network address. This is stuff that is also in the documentation. I can't go into too much detail on PyGrid, but if you want to use PyGrid and do configuration and stuff, either read the documentation here, which gives you some info, and alternatively, you can also have a look at the PyGrid documentation, which you can find on the PySift or PyGrid site. So if you have a look here and go to PyGrid, there's some docs also here, and you can read through them and and adjust the settings accordingly, so you can work with PyGrid nodes. What's important here is if you want to host a grid node, you need to pass data directory. So if you're on a remote machine and you want the node to load the data and have it ready for training, you pass the data directory. And you also need to pass the configuration file, which again we'll talk about in a second. And if the node is actually meant for inference purposes, you can also pass a mean and standard deviation file, which is the dataset statistics used to do dataset rescaling. So these are all options here. And if you don't want to go through this fast, you can do one of two things. You can use the make file, and you can, for example, create a whole ensemble of local nodes by creating or by running make grid node. So this will run, as you can see here, Alice on port 8777, Bob on 8778, Charlie on 8779, and the crypto provider on 8780. It'll load the data and it'll be ready. So this is basically just a process running, and then you can go in and do your training on these grid nodes, which are now running locally. And you can do that by running make federated grid node secure, and this will actually use the use PyGrid and train on the grid nodes. So this is the same as before. This will run just a little bit faster because of the protocol, and it'll do the same thing though and train using these grid nodes. Now, if you want to use grid nodes which are on the public web, you need to pass a different configuration file, and I'll show you how to do this in a second. Let me just clear out of this training so this doesn't take forever, and let me kill these nodes here, close this terminal so we can go on. Okay, so training on grid nodes takes this WebSockets flag for train.py, and WebSockets will go and read by default this configuration file here, websetting config.csv. Let me enlarge this so you can see. It's actually quite a simple file, and shows the git blame for some reason, VS Code. Okay, let's just do that. This will take the IDs, and you can name the nodes whatever you like. You should be careful because MNIST uses these hard-coded nodes for beginners. You can change them. You should just know what you're doing. And host name in this case was because the training connects to the local WebSocket workers, so that's 127.0.0.1, and the ports that we saw before. But if these are on the internet, you need the IP addresses and the ports, and obviously they need to have a firewall. If you're using Linux, you need to set UFW or whatever you use to allow connectivity. Otherwise, the connection will get refused. Okay, so that's that. I will not save it, otherwise the CSV will be broken. Good. So that's that, and you can do the same with insecure grid node training, and you can also do local training, which is what I said before under train.py, and it also uses the CUDA flag. So let me run this, and it'll actually warn me, or it won't probably warn me. It will just not use CUDA because I'm on a Mac, and Macs don't have CUDA support, unfortunately. So this will now use, because I passed the here for local, I passed the entire training directory. It will use the entire training set. So this is the default if you want to train a local model. Great. There's also some makefile entries, as I said, for the grid nodes, just to sum that up. If you want to create an inference setup, these are sort of pre-made. And for example, you can make a model owner. And this will just, run node for you with, we've got Python still running. Let's just kill the Python. And good. Now we can make a model owner. The port won't be occupied. because we used 8771 before. So right now we have the model owner, and this is now prepared to do inference. And you can also, if you want to do local WebSocket-based inference or HTTP-based inference, you can do this. You can run this make inference setup, which will run all of them at once. Okay, great. Before we finish up with training, let's have a look at the configuration file. The one that's used here by default is this one, pneumonia resonant pretrain.ini, which is this one. And we can just have a quick look at this file. So all of the settings for this are here in the configuration file documentation, and they are in the comments. So if you're unsure what they do, just have a look here, and this will be. They're rather self-explanatory, most of them. Some of them are commented out, and you can comment out stuff in this ini file by putting a semicolon in front of them. There's some options here for configuring the training in total. There's settings for augmentation, specific argumentation settings, which is the augmentation library we use, settings for federated learning, and settings for the system, for example, how many threads to use. This gets passed on to PyTorch. This one's quite important, the repetitions dataset. This actually means how many times the dataset is augmented by. So if you've got 4 images and you've got repetitions dataset 5, you'll get 20 images. The original 4 plus 16 augmented images, augmented with the settings above. And PriMIA will sort of adjust this a bit for you if certain settings are strange with the batch size, for example, or the number of epochs, there's a mismatch and stuff wouldn't work out. It will adjust it and it'll warn you. But it's all relatively self-explanatory if you're on the training. Great. Back to the makefile. Now let's have a look at inference. So we looked at how to do training. We looked at how to set up PyGrid nodes, and now we'd like to have a look at inference. So let's have a look at inference.py. What the options for that are, and there we go. So inference takes a data directory to classify. So if you want to use the makefile, you can do as I have done and have a .inference folder here, which is the one in the makefile, but you can pass any folder you like, of course. And I've got some images in here for classifying. It needs a weights file, which is just a PT file, which gets created, for example, when you run training. So if you've got this model weights PT file, that will work. And at the moment, this points to, where is it? Inference, there we go. Model weights, I've got this pre-trained weights folder, and there's a model in here. But you can either use one and name it that, it works, or you can just put your own. And if you want to do encrypted inference, you need to parse it specifically because it takes much longer time. Also, just a word of warning, encrypted inference, you really need a beefy system to do it. If you do it with virtual workers or with local WebSockets, it'll easily kill 64 gigabytes of memory, and it'll saturate a machine with 16 CPUs. So it's really not a joke. And if you're seeing strange behavior related to the process reaper killing your inference process, it's because you're out of memory. So you either need a really big swap file, or you need to use like a really beefy machine or a server. So if this doesn't work, you might need to downscale the images. There is actually a setting in the config file to reduce or increase the inference resolution. So this might help you if you're running out of memory. Or you need to use a smaller model. ResNet 18, 11 million parameters is about 140 megabytes, and the net amount of network I/O, because of the huge fixed precision tensors that get pushed around between the workers, is about 10 to 12 gigabytes of network I/O for one inference pass. So that's rather demanding. Also, if you've got data caps, I wouldn't suggest doing this over the internet. It will work, but perhaps you will need someone to help you a bit with setting stuff up. And if you do it over the internet or you use WebSockets, you also need this WebSockets config file. So the idea here is that you pass it a CSV file with the IP addresses and the ports, just as we did for training. And there is one provided here, and it's called configinference.csv. Let's enlarge that again. And you can see at the moment it's set up for local WebSockets workers at 127.001. And there's a data owner, model owner, crypto provider. These are the ones you can make by running the makefile entries here, or you can pass the IP addresses to real workers. And what you could do, for example, is SSH into 3 cloud servers, download the repository, and then on the first one, run make crypto provider. That will create that. On the second one, run make model owner. On the third one, make data owner, and then give the data owner the config file, the data directory for the data which needs to be classified, and this file, and it will load it, and then you put in the IP addresses here in config inference and the ports, open the firewall, and then you can run inference from your machine, essentially to make it work in an end-to-end encrypted fashion, which is rather nice. And if you do local inference, you can use CUDA as well. This won't work, obviously, if you're doing it remotely. And there's also little complication with the WebSocket protocol. So sometimes the TCP buffers get overrun when you use WebSockets, and you get some strange errors. And if you get WebSocket related errors, you can instead of using WebSockets, you can use HTTP as well. And HTTP is really very, very solid. This will work under almost any circumstance. It has a little bit of a performance hit, and it increases network I/O because of base64 encoding and not being fully duplex, but it'll work extremely well. So if you are doing stuff with the network and you're seeing problems with WebSockets, just use HTTP protocol. Okay, but if you just want to use the makefile and just experiment, that's very easy. You can do let's do an encrypted inference, or perhaps let's actually not do encrypted inference because it'll take a couple of minutes, about 3 minutes, to do one image. Let's just run like this, and you'll see what happens. This will run really quickly with the virtual workers. So if you're unencrypted, even over the network, I'll show you in a second. It'll take only a couple of seconds, and you'll get the inference results and how long it took. So let's try this out with WebSockets. You can make an inference setup like that, and this will create the model owner, data owner, and crypto provider. And then in a separate terminal again, so these are processes on your machine, and they're running in the background. If you kill this, you can put them in the background, obviously, if you know how to do it with Control Z and stuff, but you can just open a second terminal, and then you can make unencrypted inference with WebSockets, and you'll see it takes just a little bit longer with the WebSockets. So the other took under 1 second. This takes 1.05 seconds. Same result. You can also use HTTP. This will take just a little bit longer, about 200 milliseconds longer, and you can see the HTTP messages. So that took like 0.3 seconds longer. And if you go and do encrypted inference, it'll take about 3 minutes for for virtual workers, and it'll scale up with obviously with the utilization of the network, and it'll depend, of course, also on ping latency and on the network speed you have and everything. In every case, it's still very efficient. So far, PriSift has been using the the Secure NN protocol, and this this really is not very efficient. And we're using FSS, which is a new protocol that our crypto team, PriSift crypto team, developed, function secret sharing, and of course not only the crypto team, people like really great scientists at INRIA and others. So it's a product of a huge amount of work, very complicated, but it's a great protocol. It's very efficient and it runs super fast, and it even works extremely quickly if you do fixed precision encoding with 16 bits, which if you do that with Secure NN, it will probably make your computer run out of memory. So if you want to do the comparison, we have a comparison in the paper. And if you want to do the comparison, you might need to turn down the fractional precision to 4 or even 2 bits just to have Secure NN run at all. We had to run this on servers with a huge amount of memory, just so that Secure NN doesn't blow up completely. So yeah, that's inference, and that's basically everything that PriMIA can do. If you want to get involved, by all means, please do. We'd be very excited. There's some pointers here for adapting PriMIA to other use cases. For example, if you want a different network architecture, or you want to use different data, or if you want to help us port PriMIA to the next version of PriSift or a different framework, this would be very exciting to us. If you have any kind of issue, please open an issue here on PriMIA. As soon as it goes public, you'll be able to open an issue. And also, we welcome pull requests. One thing I'd like to do before I stop is obviously to point out the OpenMind GitHub, where PriSift and PyGrid are hosted, and also our site and our Twitter. So if you're interested in getting involved, please do visit the OpenMind site, and please also join our Slack. And we are a very, very welcoming and open and lovely community of people, and we welcome everyone who wants to contribute and get involved with privacy-preserving machine learning. So if you've got any questions, please contact me on Slack or one of the other authors. In fact, I'd be amiss if I didn't shout out to my great team who helped make this project what it is, and I need to call out Alex, who designed and developed nearly all of the library, our lead developer, and Jonathan, who took care of all the security and privacy stuff, and Rikma, who helped us with all of the medical data, Theo, who designed the FSS protocol or was one of the co-designers and leads the crypto team at OpenMind, Andrew, who helped us a lot with many things, and of course leads the OpenMind project itself. And there's a lot of other people at OpenMind who did really phenomenal work, and I'd like to thank all of them, because without you, PriMIA wouldn't exist and all of this wouldn't be possible. So thanks to everyone, and yeah, thank you very much for watching, and I'm looking forward to seeing you on the OpenMind Slack. You'll find me, I'll have a PriMIA logo next to my name. So that's all, and see you soon. Cheers.